So question number one, you just read the number. You just read the number off the thermometer. So the uncertainty is half the resolution, half a degree. Micrometer is it is a measurement. It is a measurement because we have to make a judgment on the zero error and then on the final value we mean. So that's plus or minus 0.01 millimeters. That's the resolution of a micrometer. Work out percentage uncertainty diameter. So the uncertainty 0.01 divided by 0.29 gives us 3.448%. To work out the area, we square the diameter or raise the diameter to the power of 2. So we multiply the diameter by the same number as the power. So here we multiply it by 2, it's 6.9%. Standard rule is percentage uncertainties to two significant figures. Work out what the area is. We want this in millimeters. Pi d squared over 4 for the area. You make less mistakes using that. Plug the numbers in and we get 0.66. That should be two significant figures because the only number we're calculating from is not a constant is the 0.29. Number 3, the volume of the block. He wants it centimeters squared, so I've converted these into centimeters squared here. I get 2.53125. I've kept that as the full value because I'm going to need that later on in the calculation, but I've written it to two significant figures because the numbers it's calculated from are 75, 75, and 45. The lowest number of significant figures out of those is 2. They're all 2, and then we give our answer to two significant figures. We then need to work out the percentage uncertainty in the length and the width and the height. And so these are measurements because using a ruler we have to line up the 0 and read the number off. So that's 1 divided by 75. Doesn't matter whether you do that in centimeters or millimeters because the units will cancel top and bottom. So we get 133 and 2.22. Now to work out the volume, what we do is we multiply all these numbers together. So we add the percentage uncertainties, add them all together and we get 4.88. Question, what's an absolute uncertainty? So what is 4.88% of 253.125? We get 12.376. Now we need to give our uncertainty to the same number of decimal places as our value, and here we've said we're only short of the nearest 10. So the sort of it's minus 1 decimal places, if you like. This number here is the last important one, the 5. And therefore that should be the last important one on our uncertainty as well. So it should be plus or minus 10 centimeters cubed. Number 4, thickness of a sheet of paper. You take the 9 millimeters, divide by 100, one significant figure because the 9 millimeters is one significant figure. And then I've done this a bit of a long way around. I've worked out percentage uncertainty is 11%, and then what is 11% of 0.09? But what you can actually do is go, well, actually the uncertainty is 1 millimeter. That's divided across the 100 sheets, which is divided by 100, so 0.01. Plus or minus, check that they are the same number of decimal places. That is 2, 0.09, and the uncertainty 0.01 is also 2 decimal places, so that's fine. Number 5. Work out the mean time period for 10, 8.83, divide it by 10. 3 significant figures for 8.83. So our answer should be 3 significant figures, 0.883. Excuse me. To work out the uncertainty, it's half the range. So you take the biggest one, 8.93 minus the smallest one, 8.71, divide by 2, and we get 0.11. Now, that's over 10 time periods, so the uncertainty in one time period is going to be a tenth of that. So our answer is 0.011. We put that together with our value, 0.883 plus or minus 0.011. And we can see the same number of decimal places. They're both 3 decimal places, so that's fine as well. Now, number 6, the length of the wire. You always need to think about the context which the experiment's being done in. The resolution, the uncertainty here, strictly speaking, is 1 millimeter. But you need to think that if it's a kinked wire, you're going to be less accurate than that. So you need to make some judgment about what the uncertainty in that would be. AQA seem to think that 2 to 5 millimeters is reasonable in this, so I tend to agree with that. Another example with this would be sort of dropping a ball with a timer. It's a measurement. The resolution of a timer is 100th of a second, so your uncertainty should be 0.01. But there's no way you can time that to 100th of a second. You've got the human reaction time in there as well. So I would argue that is probably about a tenth of a second for that one there. Number 7 really highlights why we use trigonometry and not a protractor to measure angles. It is a measurement. We have to line up the 0 and read the measurement off. So it's the resolution. So it's plus or minus 1 degree. To work out the sine, opposite of hypotenuse, 34.9 degrees. Both the values are 3 significant figures. So our final answer should be 3 significant figures, hence 34.9. To work out the percentage uncertainty, they're measurements because we've had to line up with a ruler. So the uncertainty in centimeters is 0.1 and our readings are 10.7 and 18.7. So our percentage uncertainties come out at 0.93 and 0.53. When we work out the sine, we divide one by the other, and when we divide two quantities, we then add the percentage uncertainties, so we get 1.469%. We're going to assume the percentage uncertainty in theta is the same as percentage uncertainty in sine. Here it might be just worth bearing that in mind for any mathematical function in the exam. Learn, for instance, exponential, but I've not seen it come up in an exam before. So what is 1.469% of 34.9 degrees is 0.5128 degrees. Now we need to quote our value and our uncertainty the same number of decimal places. Our 34.9 is three significant figures from the values it's calculated from. And importantly here, 1 decimal place. So we need to put our uncertainty to 1 decimal place, which is half a degree. So you can see that is a much, well, it's got half the uncertainty that the protractor has there. Thank you.